going to talk about trigonometry. We've already talked about the Pythagorean theorem, and I told you that the Pythagorean theorem caused mathematicians to be invented. Before then, we were just basically calculators. We would add up 6 buckets of wheat. You eat 1 bucket of wheat, 6 minus 1. You now have 5 buckets of wheat. That was all math was before the Pythagorean theorem, but the fact that the Pythagorean theorem worked got people thinking, and they started looking for other patterns, and those other patterns led to all sorts of new mathematics. And what we're going to study today is sort of a result of the Pythagorean theorem, and it's more useful, really. Pythagorean theorem only has a couple of uses, but we're going to be studying trigonometry. So, trig, or tri, meaning 3, gonometry, meaning the mathematical study of. Trigonometry is the mathematical study of 3, more specifically, triangles. We talked about right triangles. So our favorite right triangle is the 3, 4, 5 triangle. And the Pythagorean theorem says that 3 squared plus 4 squared equals 5 squared. Now, if we had a triangle that was half as big, it would be 1.5, 4, and 2.5. If we had a triangle that was twice as big, and I can't really draw it to scale, or sorry, apparently I don't know how to divide by 2. Does that make you feel better? Thanks. You guys are judging me. Quit judging me. If I had a triangle that was bigger, it could be 6, 8, and 10. There are probably an infinite number of triangles that have nice numbers, right triangles that have nice values. Those are called Pythagorean triplets. 3, 4, 5, 8, 12, 13. There are lots of them. So, looking at these, there are other patterns that we start to notice. The obvious one is if you take any side of the big triangle and divide it by the corresponding side of the little triangle, you get the same number every time. 6 divided by 3, so if I divide those two, I get 2. 8 divided by 4 is 2. And 10 divided by 5 is 2. That's sort of an interesting pattern. You double the size of the triangle, the shape is exactly the same, and the side lengths are proportional. Now, if the triangle was 3 times as big, if I did all of those divisions, I'll end up with the same numbers. And that is an idea that is linked to the shape of the triangle. In fact, any triangle the same shape will have a common ratio among all of its sides. So if it's 4 times as big, then all the ratios would be 4. And that got people thinking, there's more to this. The numbers inside those triangles are linked to the shape of the triangle. So, let me do a quick calculation. One of these angles is 53 degrees. So this one is 53.1 degrees. And the little one happens to be 36.9 degrees. The common aspect of all of these triangles would be the angles. In the small one, the medium one, and the big one of the angles is a right angle, one of them is 36.9, and the other is 53.1. Every single triangle of that shape will have proportional sides. Just the ratio will change according to how big it is. If it's 4 times bigger, then the ratio will be 4. If it's 8 times bigger, the ratio will be 8. But what if I compare the triangle with itself? Instead of comparing 2 different sizes of triangles, what if I looked at each triangle individually and compared those sides to themselves? So what if I take the smallest side and I divide it by the second smallest side? I get 3 over 4. What about this? 1.5 divided by 2. Somebody pull out a calculator. What is 1.5 divided by 2? 0.75, which is 3/4. Okay, what about the big one? What about 6 divided by 8? It's 0.75. What if the triangle was much bigger and I had 30 divided by 40? 0.75. That's an idea that allows us to study the relationship between the sides and angles of a triangle, and thus trigonometry is born. Now, you're not going to appreciate how nice it is, but what that's saying is 3 divided by 4 is linked to the shape of the triangle, not the size of the triangle. I have 3 different triangles, all that have the same shape. They all have the same angles. The sides are different lengths, but when I divide the short side by the middle side, I always get 0.75. And that leads us to believe, the ratios of the sides of a triangle, any side of a triangle divided by any other side of a triangle, has everything to do with the shape, the size of the angles, and not the size of the triangle. Okay? So this angle guarantees that small divided by middle will end up being 0.75. Any right triangle that has that angle will have that characteristic. Okay? Well, how many different ratios are there? Let's go back to my original 3, 4, 5 triangle. How many different ways are there to divide the sides? 3 over 4 is one. What other divisions could I perform with those 3 sides? 3 over 5, 5 over 4, 5 over 3, 4 over 5, and 4 over 3. That's it. There's 6 of them. Now, all 6 of those ratios are going to be the same as any other triangle that has that same shape. So if the numbers are always the same for every unique triangle, we're going to give them names. There are only 6. All 6 of them have names. That way, instead of saying, ratio 1 and ratio 2, ratio 3, or saying big divided by middle or small divided by middle, stuff like that, we just give them names. 3 of the names are really common. 3 of the names you may or may not have ever heard of and probably aren't going to use very much. There is one problem, though. The hypotenuse is always referred to as C in the Pythagorean theorem, and the legs, the 2 short sides, are A and B. Does it matter where A and B go? No. So 3 could be A or 3 could be B. And that causes a little bit of a problem because A and B could be switched. So when we talk about ratios, we need to link the ratios with specific angles. And the way we do that is whatever we call A is opposite or doesn't touch an angle that we refer to as capital A. And whatever side is little b, the angle opposite, or the one that doesn't touch it, is referred to as capital B, and the right angle is always capital C. When we name the ratios, you have to state the name of the ratio. You also have to state the name of the angle you're looking at, just so we don't have an A-B mix-up. Okay? So if I have a right triangle, we're going to pick one of the 2 angles, and we'll call it theta. Theta is just a Greek letter. In the Greek alphabet, you have alpha, beta, gamma, delta, epsilon, zeta, eta, theta. What's that? Feta is It's also Greek, though. You're in the right country. Feta, feta is a Greek cheese made out of goat's milk. It's pretty strong. Although, if you buy feta in the United States, it's probably not goat's milk. It's probably made out of cow milk, but you goat or sheep, one of the two. So, when you name these ratios, you have to pick one of the angles, and you're never allowed to pick the right angle. You have to pick either angle A or angle B, and they might have other names, but you cannot pick the right angle. And then the longest side is always referred to as the hypotenuse. To distinguish between the two legs, we just describe the side that touches theta and the side that doesn't touch theta. So there are two legs left. One of them touches theta and the other doesn't. We call the one that touches theta adjacent. The word adjacent just means next to. So whatever leg touches theta is called the adjacent. The leg that does not touch theta is referred to as the opposite. But, once again, I can move theta to the other side if I want. If I drag theta up here, how does that change the naming of the triangle? The O and the A will switch. And it doesn't matter what angle you pick. Usually the angle will be told to you. They'll tell you which angle to pick. But there are ways to work around it. It doesn't really matter which one you pick. And now we can give you the names for all of the ratios and how they work. So the name of the first ratio is sine. S-I-N-E. It's abbreviated S-I-N, and if you say sin, we'll laugh at you. Yeah, and the way that trig works, you state the ratio's name, and then you state the angle that it's using. So in this case, we've labeled theta. The sine of theta is defined as the opposite side divided by the hypotenuse. So sine is the ratio you get by dividing the opposite angle, the opposite side, by the length of the hypotenuse. The next ratio is referred to as the cosine. It's abbreviated COS, and it is defined as adjacent over hypotenuse. To calculate the cosine, you take the length of the adjacent side and divide it by the length of the hypotenuse. The next one is tangent, and it's abbreviated TAN, and defined by opposite divided by adjacent. Those are the three basic. The other three are just the reciprocals. So if you take sine and you flip it upside down, H over O, and H over A, and A over O, those are the other three ratios, and the names are cosecant, secant, and cotangent, and we're not going to mess with those in this class. So there are three other ratios. Your calculator doesn't even have a button for them. But if you know what the sine is, it's really easy to calculate what the cosecant is. So you don't need a button on your calculator for it because the three buttons you have are enough. In fact, one button is technically enough. If you had one of the three, there are ways to figure out the other five. It gets a little bit more complicated. So 3 buttons is ideal. There's a way to remember this. Does anybody know SOHCAHTOA? SOHCAHTOA lays out sine, cosine, and tangent. Sine is O over H, cosine is A over H, and tangent is O over A. If you can remember SOHCAHTOA, then you have the ratios for sine, cosine, and tangent laid out right for you. Let's go back to our 3, 4, 5 triangle. Erase some of this. Let's call this side A and B, 3, 4, and 5. If I wanted to know what is the sine of A, what would the ratio for the sine of A equal? angle theta is going to be placed up here. Sine is O over H. O would be the opposite side, so if you look at angle A, which of those values is opposite angle A? 4. 4 over. And which is the hypotenuse? 5. Now, I think the front side of your worksheet wants the fractions, and the back side of your worksheet wants the decimal. So you 4/5, or you could type in 4 divide 5 in your calculator, and it's going to spit out 0.8. All right, what about the tangent of B? Tangent is defined as O over A. If you look at angle B, what would be the opposite side? 3. And the adjacent side would be 4. So the tangent of B is 3 over 4. And you can divide that in your calculator, and you end up with 0.75. Okay. What about the cosine of B? If you look at angle B, cosine is A over H. What is the adjacent side for angle B? 4. And the hypotenuse for angle B would be 5. That looks familiar. Why is the sine of A equal to the cosine of B? I guess it depends on what you mean by opposites. But why is the cosine of A always going to be equal to the sine of B, or the other way around? Sine of A equals cosine B. So if I put theta down here, O over H would be 4/5. But if I put theta up here, A over H is still 4/5. The reason is the opposite side for A is exactly the same as the adjacent side for B. So that's something that you want to remember. The sine of A is always going to be equal to the cosine of B. They're the same thing. If you move theta, then the O and the A switch. Okay? Well, remember I told you that this is 53.1 degrees. So the sine of A is always 4 over 5, no matter how big the triangle is. If the triangle is 10 times bigger, or if it's much, much smaller, as long as the angles are the same, the ratio is going to be the same, which means the calculator knows what the answer is going to be without even looking at the triangle. It turns out it's a graphable function, and you can just ask the calculator what it's going to be. So if I go to my calculator, and it's actually 53.13 degrees. If I ask the calculator what the sine of 53.13 is, I should get about 3/4. Now, there's more decimal on there, so we're going to be off by a little bit. But everybody turn your calculators on. And you have to make sure that your calculator is in the right mode. There are two ways to measure degrees. One of them is degrees. The other is called radians. And radians are really good in the mathematical world, and they're practically useless in the physical world. In order to make sure that your calculator is in the right mode, everybody push mode, which is next to the blue second button. And the third or fourth line down, you get to choose between radians and degrees. You want to be in radians. No, sorry, you want to be in degrees. Make sure your calculator is in degrees. Then when you exit out, what is the sine of 53.13? And I should get 0.75. Or no, 0.8. That's what we wanted, wasn't it? Oh, right here. 0.8. Why is that off a little bit? Because the angle is actually 53, right? 53.13010235. So your calculator knows what all the ratios are, and you guys don't understand how important this is, but no matter how big the triangle is, if angle A is 53.1 degrees, then the opposite side divided by the hypotenuse will always be 0.8. And the fact that that's true allows us to do all sorts of mathematics that, if it wasn't possible, would make our lives much, much more difficult. So on your worksheet today, on the first page, it says find the value of each trigonometric ratio. You'll go through and it tells you which angle to look at, the tangent of z, the sine of c, and so on. If you turn to the next page, same basic idea, but whatever fraction you get, instead of simplifying the fraction, plug it in your calculator and write down the decimal. And then for 19 through 22, there is no triangle, but you don't need a triangle. All you have to do is type those values into your calculator and it will spit out the correct decimal, and then you have two critical thinking questions. Okay, that's your assignment today.